Okay, we've introduced sequences, series, and sequences of partial sums. So we're going to look more closely at sequences and talk about what's called convergence. Convergence of sequences. What's that? So convergence is and divergence is kind of the main topic when you talk about these sequences and series. So we're going to just focus on sequences today. What does it mean, sequences being converging or diverging? Okay, so an infinite sequence converges if all the terms after some place in the sequence, so you get to some place in the sequence, all the terms after that are essentially indistinguishable from each other. Meaning we've kind of landed on we're getting really, really close to a value. And you can pick any degree of closeness that you want to that value, and you'll get to that degree of closeness, and then more close. So pick any degree of closeness that you want, okay? As long as you go far enough out in the sequence, you'll achieve that degree of closeness to this value, and then do better than that after that. Does it make sense? So if an infinite sequence converges, it's said to have a limit. Meaning there's this value that the terms are getting closer to, and then as close as you want, as long as you go far enough into the sequence. Again, so there's this value L that the terms are getting close to. Pick any degree of closeness to L. Eventually, if you go far enough out in the sequence, your terms in the sequence will get that close to L and then get closer after that. Pick a higher degree of closeness. If you go out far enough, you'll achieve that degree of closeness and then get closer. All right? So it's the idea of a limit. So that as I gets really large, these terms are honing in. Like you think of it, honing in as close as you want to this value, the limit. So let's look at the, so otherwise, any other case is the sequence diverges. Any other thing that happens, the sequence diverges. So that includes things like the terms just getting really big as just getting bigger and bigger and bigger. Or jumping around, right? If the sequence just keeps jumping around and never hones in on a particular value, that means the sequence diverges. So any other thing besides the terms converging on a value is that the sequence diverges. All right, so from Monday, we had this one. 2i minus 1. Remember 2i minus 1. 1, 3, 5, 7, 9. Does it converge or diverge? Just gets big, right? Just keeps getting bigger and bigger and bigger. Clearly diverges, right? This one. So negative 3/4, 5/9, negative 7/16, 9/25, negative 11/36. So if we look at these terms, so you think about the decimal approximations might help. 0.75, close. These are kind of close to a half. Now we're kind of around. Now we're getting like a third. And if we look at what's happening, or what the formula was, we had 2i plus 1 over I plus 1 squared. So as I gets very, very large, what happens to these fractions? Because, yeah, so I plus 1 squared versus I to the first, basically, right? So the denominator is going to eventually get much, much, much larger than the numerator. Okay, let's be a little more formal about that. So we can multiply out that denominator. We could multiply out that denominator, and what's that? I squared plus 1, right? I squared plus 1, right? I plus 1 quantity squared, I squared plus 1. If you're nodding, no. Right? Middle term, I squared plus 2i plus 1, right? I plus 1 squared does not equal I squared plus 1. Equals I squared plus 2i plus 1. Okay, and so what we've really got here, now we're looking at the limit as I gets really large. And so this is a precalculus problem. That's a rational function. You have a rational function there, and this is a precalculus problem. And one way to approach this, so this is like talking about, is there a horizontal asymptote? Or what's the end behavior of this function, right? What's the end behavior? If this was 2x plus 1 over x squared plus 2x plus 1, then as x gets really large, what's the end behavior? Does it go off to infinity? Does it have a horizontal asymptote, or does it get close to 0? Remember that from precalculus? And so that was about comparing the degree of the numerator and the denominator. So what's the degree of the numerator? 1, I to the first. What's the degree of the denominator? 2, I squared. So in the case where your degree of the denominator is greater, do you remember what that limit is? 0, right? So if the degree of the denominator is bigger, then that gets much, for large values of, in this case, I, that gets much, bigger than that, and so that limit is 0. What if the degrees are the same? If the degrees are the same, do you remember what happens? Yeah, so all the lower degree terms just go away, right? So for big values, so if this was 2i squared plus I, so I'm just going to change the problem for example's sake. So if it was 2i squared plus 1 over I squared plus 2i plus 1, then as I gets really large, all this stuff kind of fades away to nothing. Plus 1, 2i plus 1. And then we're left with, for large I, we have 2i squared over I squared, which approaches 2. So it ends up being the ratio of those leading coefficients. And then what if the degree of the numerator is bigger than the denominator? So what if this was 2i cubed? Then this thing just gets big, right? The numerator gets much larger than the denominator, and this thing just approaches infinity. So you have those. You're going to see a lot of these rational functions in these limit problems, and you're going to approach them the way you approached what in precalculus, end behavior of these rational functions, meaning, and that's all having to do with comparing the degree of the numerator and denominator. Okay, so that just reinforces that this. We had degree of the denominator greater, therefore that limit is 0. So this one converges or diverges? Converges to 0, right? So all these terms get as close as you want to 0 eventually. Pick any degree of closeness, go out enough terms in the sequence, you'll achieve that degree of closeness, and then get closer than that after that. Converges. All right, last one was this example from last class. We had 2 to the I minus 1 over I. So 1, 4/3, 2, 16/5. So let's take it just, again, decimal approximations. 1 1/3, 2, 3 and change. What? 5 and change. 8 and change. So what is this? Clearly getting large, right? So exponential functions, 2 to the I minus 1, that's gonna dwarf I in terms of getting large, right? So exponential functions, we know, with the right base, get very big, very fast, much bigger than say I. So that certainly diverges. That gets really big. Okay, so those are just some startup examples to get the idea of it. Any questions so far? Okay, so some common forms. The first common form that we're going to see a lot is what we're going to call a P sequence. A P sequence. If you have toddlers like me, you know all about the P sequence. Okay, 1 over I to the, not this P sequence though. 1 over I to the P. 1 over I to the P. And we want to say, for what values of P, I is our index, right? So what is this? 1 over 1 to the P. Comma, 1 over 2 to the P, 1 over 3 to the P, 1 over 4 to the P. That's the sequence, right? Because I is our index. For what values of P does the denominator get really big? And therefore, the reciprocal would get really small. Okay, so for what values of P? So let's write out the first 4 terms of each sequence. and ask by looking at those 4 terms. So here, this is a common technique that you'll use. Is just write out some terms and just look at what the terms are doing. That can give you a lot of information and evidence towards whether it converges or diverges. So everyone go, write out the first 4 terms of these for practice. Because remember, a sequence is a list. So whenever you see something like this, you have to imagine, oh, this is a list of values. You should be able to create it. So go. You don't have to solve it simple. You don't have to simplify it in your head. You could just tell them exactly what it is. Yeah, if you don't know what that is. But what is that? 64. Okay, but that's fine. If you can't do something, just then express it, right? It's fine. Okay. Converge or not? Yes, definitely. Sorry. Yeah, that clearly converges to 0, right? So clearly these numbers are getting big fast. Okay, 1 over I to the 1/2. Anley, did you get that? So not 1 over 2 to the negative 1/2. So it's positive in the denominator. So yeah. Okay, and then yeah. Okay, good. And then on and on and on, right? So really, this is 1 over root 2, right? 1/2 power is root 3. Root 4 is 1/2. What about this? What about 1 over, so eventually we'll get to I equals 10, right? That'll be 1 over, or say 100. I will get to 100 and we'll get to 1/10 when I is 100. When I is 1,000,000, or 10,000, when I was 10,000, 1 over 100. What do we think? Yeah, it goes to 0, right? It just goes a lot slower than the first one, right? It takes a lot more terms to start getting close to 0 than that first one, which is 1 over I cubed. But even this fraction exponent, eventually with the large I, that denominator is going to get large, right? What about 1 over I to the negative 1/2? Adam, did you get that? Uh-huh. How about this? It really diverges. This is getting huge, right? This will get big. So, because this is essentially, when you have a negative exponent, that's essentially the same as, or it is the same as, that. So for what values of p, if we just take these 3 examples, can we make a conjecture? For what value of p, what values of p does that denominator get really big? And so the 1 over I to the p gets small. Greater than 1? Yeah, anything positive, right? So even this, right? So this is the kind of the most important example. Even if it's just as long as it's positive, eventually you make I large enough, that denominator is going to get large for any positive p exponent in the denominator. Okay, but so clearly when p is negative, then we don't really have a fraction anymore, and the numbers just get big. Okay, so p sequence. For what values of p does 1 over I to the p converge to 0? Anything positive, p greater than 0. So here's how we state that. Thus, 1 over I to the p approaches or has a limit of 0 as I gets large if p is greater than 0. So the P sequence, we'll see it a lot, and we'll see it combined with other things. So we'll see it just by itself, and we'll see it combined with other things. So we have to be on the lookout for the P sequence. Questions on that one? Okay, another one. Geometric sequence. Geometric sequence has this form. R to the I. Okay, R to the I. So now your index is your exponent. Remember before, your index was the base. So see, again, compare the difference here. Totally different. Totally different. The example we just did, the P sequence, P was the exponent in the denominator. And our index was our base, meaning the thing that changed as we went from one term to the next, I was the base. Now here, the base is some constant value R, and as we go from one to the next, the exponent changes. Totally different animal. Make sure you have those straight in your mind. So this is called, when it's this way, it's just called the geometric sequence. So we want to kind of do the same kind of analysis. For what values of R does R to the I get really small, get really big, stay constant, do something else? So here's a bunch of examples. We want to, again, write out the first four terms of each of these. Be efficient, okay? Write out the first four terms of each of these. Okay, here we go. Ruth, tell me about the first one. Oh, she said always one. Agree? Is this converge or diverge? Yes, it converges to 1. Because pick any degree of closeness to 1, you get to that degree of closeness, right? Like perfect closeness. It is 1. So yes, so a string of 1s converges to 1. All right, how about the next one? Julie. Dot, dot, dot. Agree with that, everyone? Okay. Converges or diverges? Diverges, clearly. Okay, so notice when R is 2, diverges. Okay, next one. Edmund. Three to the fourth over 4 to the fourth. So what's the general idea behind a geometric sequence now that you've written out a bunch of them? What's happening when you go from one term to the next? What's the idea to get to the next term? What's happening? What's that? Okay, yeah, so to get to the next one, you just multiply by one more R, right? You keep multiplying by one more R each term. So R to the first, and then R times R, then 3 R's, then 4 R's. So you take the last one and multiply it by your first one, R. That's right. So what happens if you keep multiplying by 3/4, 3/4 times 3/4 times 3/4, and you keep taking 3/4 of your last term? It's just gonna, right, so this is going to approach 0. Okay, next one. Stone. Did you get this one? Right? Right? Keep multiplying each time by what? You keep multiplying by -1/5 over and over again. Diverge or converge? Converges to 0. Okay that it's alternating? Yeah. So it's honing in on 0 just from 2 places, right? It's honing in from below and from above. But it's still honing in on 0, even though it's alternating negative, positive. Negative 3 to the I. Converge or diverge? Diverge. So this is like as bad as it gets, right? Because part of your terms are getting really big by multiplying by 3, and then the other half of your terms are getting really, really big negative by keep multiplying by negative 3. So it's like splitting off to negative infinity and positive infinity. As bad as it gets, right? Divergent. What about this? Negative 1, 1. Negative 1, 1. Negative 1. Does that converge to negative 1 and 1? Diverges. Diverges, right? So what is the limit of a sequence if it converges? It's the single number that all the terms get any degree of closeness to. So if it's getting close to 2 numbers, this is not convert. This doesn't converge, all right? So this is divergent. Well, all right. So when does R converge? What has to, or sorry, when does the geometric sequence converge? When R between 0 and 1? What about this one? Between negative 1 and 1. So if it's some kind of fraction of 1, right? Either negative or positive, it converges to 0. But then there's one more case where it converges. If it equals 1, but it converges to 1 in that case. So as long as it's a fraction of 1, positive or negative, so between negative 1 and 1, you keep multiplying, you're going to head to 0. If you're outside of 1 and negative 1, it gets big, right? It gets big. And then if it equals 1, it's kind of a special case that converges to 1. It's kind of a trivial case, right? They're just all 1s, right? They're just all 1s. All right, so let's summarize that. So this thing converges to 0 if, what do we say? If R is between negative 1 and 1. It's like if you keep multiplying by the same fraction over and over again, it's just going to get really small. Keep multiplying by a fifth. Keep multiplying by 9/10. Keep multiplying. So I don't know if calculators do this, but old school calculators, when I was little, you could just keep hitting times, 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 times. You pick a number and just keep hitting times, times. And it would do this thing. And then, you pick 7/8 and times, times, times. Eventually, your screen would reach 0. Okay? That's exactly what's going on here. All right? But then we have this trivial case. If R is 1, then the sequence is 1. But it's not really an interesting case because it's just a sequence of all 1s. Makes sense. So you really have to understand and file away this difference between a P sequence and a geometric sequence, right? P sequence, your I is the base, right? 1 over I to the P. And in the geometric sequence, it's R to the I. Your index is the exponent. Questions on those two? So these are common forms that you're on the lookout for. They show up all the time, and then they become involved, like they could become part of other problems, like they're involved in other problems. All right, so here's some tips. Analyzing sequences. First of all, like we said, be on the lookout for geometric and P sequences. Okay, use function limit techniques. We already talked about the properties of rational functions, right? Comparing the degree of the numerator and the denominator, and evaluating limits that way. So I already did that example. All right, there's something called L'Hopital's rule. And L'Hopital's rule says that the limit, that the limit of function of I, f, say of I over g of I, is the same as the limit of the quotient of their derivatives. So this is not the quotient rule, right? The quotient rule is something totally different. This is you just take the derivative of the numerator, you take the derivative of the denominator, and you look at that. And that has the same limit as the limit of your original quotient if you have if you have indeterminate form. If this thing is what's called indeterminate, which is infinity over infinity or 0 over 0. So if you analyze, you have some sequence that looks like one function divided by another, one sequence divided by another. And if you look at the limit of that and you get infinity over infinity or 0 over 0, then L'Hopital's rule applies. You can take the derivative of both the top and the bottom and analyze that limit, and it'll be the same as the limit that you had to start with. Because infinity over infinity, that could be 0. So these indeterminate forms could be 0 or could be a constant or could be infinity. You don't know. You don't know. So different problems have different solutions. So the way to tackle that is take the derivative of the top, derivative of the bottom, and that resulting fraction would have the same limit as the one you started with. Yeah. No, because if the top is going to 0 and the bottom is going to infinity, that goes to 0. And if the top goes to infinity and the bottom goes to 0, that goes to infinity. So those aren't indeterminate. Indeterminate is when it's like they're both the top and bottom get big. Well, different things could happen depending on the problem. But if your top's going to 0 and your bottom's going to infinity, that goes to 0. So that's not indeterminate. Okay. So that's L'Hopital's rule in a nutshell. Okay. List out several terms. We've done that. So that can help. Just gives you some evidence. All right? You need algebra. You need things from your past, from before calculus. And then there's just like some deductive reasoning and logic. You kind of this kind of goes along with listing out several terms. You're looking at kind of make reasoning or giving rationale about the sequence that you have. Okay? So that does come into play. So these are all this is all things that should be in your toolbox for analyzing sequences. So we got a bunch of examples here. Okay. So I'm going to take attendance. So go ahead and first of all just write these down. And again, you're on the lookout for P sequences, geometric sequences, and then you don't have to reinvent the wheel on those, right? So we did the development of those. You can apply what we learned, right? So when does a P sequence converge to 0? When P is? Remember? Greater than 0. So then you can just declare, this is a peak sequence, P equals 4, which is greater than 0, therefore it converges to 0. You don't have to reinvent the wheel. So you're on the lookout for P sequences, geometric sequences, and then you're just using other. Okay, so here I'm doing the easiest ones here. What does P equal in this one? The very first one is a geometric series. We're outside of that -1 to 1 range. We're -4, diverges. Okay? But you could confirm very quickly by just listing out some terms. Okay? This one is a P sequence. I think we already did it earlier today. P equals 1/2. Converges, right? As long as P is greater than 0, it converges. Yeah, so the P sequence always converges to 0. Yes, you should. Whenever you can say what it converges to, yes, put what it is. So that converges to 0. The P sequence, yep. This one diverges, right? It never does not converge to 3 values. Convergence means it gets close to a 1 value to any degree of closeness that you want. So if it keeps jumping for infinity, if the terms just keep jumping and jumping, divergent. That diverges, okay? This one is a P sequence. This is the same as 1 over I to the 4th. So this is a P sequence with P equals positive 4. Are we good on those 4? Okay, what about this one? So here we have sine of a rational function. So we can just hone in on this rational function to start with. As I gets big, what happens to the stuff in parentheses? What does that approach? 1/3. We have equal degree, numerator and denominator. So this thing gets really, really close to 1/3. Therefore, the values of the sequence get close to sine of 1/3, right? So if the inside the sine is getting closer and closer to 1/3, then those terms are actually getting closer and closer to sine of 1/3. So this converges to sine of 1/3. Make sense? Okay, how about this one? So again, just look at what's happening underneath the square root. I to the 4th minus 5 over 6I cubed plus I plus 2. Rational function. How do the degrees compare? The degree of the numerator is bigger. Therefore, that fraction gets really, really large, right? The degree of the numerator is greater than the degree of the denominator. So that fraction just will diverge. What about the square root of those numbers? It's not going to help, right? It'll make it get big slower, but it's still going to get big. This diverges, right? Diverges. These will get infinitely big. Okay, what about this? Pi to the I over 3 to the I. Because it's the same as? This is geometric because it's the same as pi over 3 to the I. You see that? So your rules of exponents are going to be crucial in the next couple of weeks. So we're going to see them all the time. So we'll review those, but not today. But we will do some review of those. So this is pi over 3. Is that in our interval for this thing to converge to 0? No, pi over 3 is a little bit greater than 1, right? A little bit greater than 1. Therefore, diverges. Okay, what about this one? So what is 3? Here's really important. What is 3 to the I plus 1? What does that mean? So what does 3 to the I mean? So it's really important that when you see that, you think what? You see 3 to the I. What does that mean? What is the meaning of that? No, just forget about everything you've learned today, all right? This has nothing to do with sequences or converging or anything. 3 to the I is saying what? Mathematically, what does that represent? What does it mean? What's that? Right, multiplying 3 times itself. How many times? I times. You've got it. So when you see 3 to the I, you think, oh, that's a bunch of 3's multiplied together. How many 3's multiplied together? I of them, right? I number of 3's multiplied together. So that's your image of 3 to the I. 3 times 3 times 3 times 3 times 3. Well, when do I stop? Well, when I've reached I of them. When I've I 3's multiplied together. So then what would 3 to the I plus 1 be? How would it compare to 3 to the I? 1 more 3 multiplied, right? So isn't it the same as 3 to the I, what? Times 3. Because now it's I plus 1 3's multiplied together. So that's the same as the one we had above times 1/3. So it's 1/3 times the one we had above, pi over I, 3 to the I. Converge or diverge? It's the same as the one above. It's just all the terms are multiplied by 1/3. So it still is going to be diverged. So it diverges. I need to show you 2 more examples so you can do your homework. Does that make sense? So the fact that it's 3 to the I plus 1, all that does is multiply the one above in the denominator by a 3. And that doesn't help it converge. That just means it gets big 1/3 as fast. All right? That just means it gets really, really large, but just 1/3 as fast. Questions on any of these examples? All right, I want to show you 2 more. So this one, 2 to the I plus 1/2 to the I. Converges or diverges? So, what about just 2 to the I? Diverges. What about 1/2 to the I? Which one wins? So, you're basically taking a divergent, diverges, and you're making each term a little bit bigger. So even though this converges to 0, adding them together, this, so for very, very large I, you're basically going to have 2 to the I plus a very, very small number. Definitely diverges, right? 2 to the I dominates. So when you're adding convergent sequences that are some converge, some diverge, the ones that converge don't help. Okay? So be on the lookout for that. What about this? So a technique that you should notice here is if you have a single denominator, you can then break it up into 2, like the previous one. That's only, you can't break up denominators. You can break up numerators with a common denominator, right? You can break up numerators with a common denominator. So we have that. So ln of I, so ln of x looks like that. It gets big. So what about this? Convergent or divergent? This gets big, right? This goes to infinity. This converges. What about this? Well, this is infinity over infinity. What can we use? L'Hopital's rule. So L'Hopital's rule says that the limit of this is the same as the limit of the ratio of the derivatives. Derivative of 3i is 3. Derivative of ln of I is 1 over I, and that equals. So the limit of that ratio is the same as the limit of 3i. Diverges. Conclusion for this one? Diverges. You're adding one that diverges with one